Assalamualaikum and a very good day to other panel. My name is Fatin Syahirah binti Muhammad Shahril. I'm from SKMM Mechanical Engineering and study at University Technology Malaysia. My supervisor is Encik Ahmad Safri bin Zainuddin. Today, I would like to present about my topic regarding to the structural analysis on WeldNet Flange and Optimized tool. During this presentation, I would like to brief and explain more deeply about 5 chapters regarding chapter 1 until chapter 5. So let's get started. Our chapter 1 is about the introduction that consists of background, problem statement, objective, and scope. So what is flange? Basically, flange is the most and main component that attached to the pressure vessel. The flange is located at the top head of the pressure vessel as you can see in the figure to remove or clean the internal part of the pressure vessel. In our topic, the type of flange that are used is the Weld flange. As seen in the picture, number 1 is the Weld flange that literally attached to the number 3, which is the vessel or shell of the pressure vessel. The flange and vessel will be connected through welded, as we can see at the area of part number 2. Basically, number 2 is the welding area to join the flange and also the vessel. Next, we move to the problem statement of these cases. Generally, the flange that are used is the standard sizing, where we refer to the SME B60.5, where it states all the dimension of the complete flange. However, due to the larger size that exceed the limit of 24-inch in SME B60.5, the manufacturer need to design by themselves as manually. Thus, this actually increased the workload of the manufacturing to design the flange that have variety of dimension, and is actually have a high tendency to cause many problems to produce the safe and optimized flange when we use the manual designing. So, the objective of this project is actually once to develop a tool for determine a safe and optimized design of WellNet flange after comparative study had been achieved between analytical analysis and finite element analysis to validate the result. Then we move to our scope. So what is our scope? Our scope is actually I want to calculate stress using analytical analysis by pressure vessel handbook. Next, I want to develop a 3D model of flange and analyze by finite element method using ANSYS. Thirdly, I want to compare the result between analytical analysis and finite element analysis to validate the result. And lastly, I will develop a tool to design the customized flange without manual designing. That's all from chapter 1. Next, we move to the chapter 2 that consists of the literature review that state the past reference and the past journal that help and contribute to my project. So firstly, according to the PV handbook, Kanti K. Mahajan had done manually calculation of WellNet flange to design the flange successfully. Next, for the past journal, Lewis had done project by varying different kind of parameter flange using both method of SME code and finite element analysis. Then he will find the maximum axial bending stress, radial stress, tangential stress for internal pressure were determined. And lastly, I refer to the past journal from the bench where it have undergo the project with different surface profile such as variation in flange thickness and were observed to obtain the stress value in the flange while maintaining other dimension for hub length and hub stress. As you can see in the picture, the sponge actually vary the thickness of the flange but still maintaining the hub length and hub thickness. Thus, for my project, based on this literature review, I have done 2 flange of different thickness of thick and thin flange to validate the result between both method of ANSYS and ASME. That's all from chapter 2. Next, we move to the chapter 3. It's about the methodology. Firstly, before we start method, we require parameter as input data to every method. According to this table, the most important parameter is independent data that need from the client specifications such as design pressure, design temperature, and flange material. Then, data from the vessel that used to design the flange such as different using diameter inside flange, corrosion allowance and thickness of the small end. So this data vessel is actually similar with the flange of the we want to design. And lastly, I analyze both methods using two different thickness of flange of thin and thick to validate the outcome. Next, after identifying all the parameters, we will explain about the method in the SME. So first step, based on the flowchart, firstly, we can input the initial parameter. And secondly, we calculate the load for hydrostatic and gasket. Next, we calculate the moment arm. Then we calculate for the component moment due to the load. And we analyze using the two flange thickness of thin and thin. Then we calculate for the shape constant. And lastly, we calculate for the stress calculation that we analyze at the end. That's all for the flowchart and step in the SME. Next, we move to the flowchart and how we want to use the method of ANSYS. So due to this flowchart, firstly, we create 3D structural flange for both thickness of thin and thick flange. Then we apply boundary condition where we have a fixed point, fixed support at the chamfer neck where it attached to the vessel. Then we apply load and pressure, internal pressure inside the diameter. Then we can generate the mesh. And lastly, we will find the stress calculation of the analysis. So that's it for the method that you use in this methodology. First for analytical analysis and second for the finite element analysis. That's all for this chapter. Next, we proceed to the chapter 4. It's about the result and discussion. Firstly, I will show the result of the SME based on thick flange and thin flange. After we done the calculation for thick flange, I identified that the stress between longitudinal, radial and tangential stress have produced value that below the allowable stress of low alloy materials steel of 155 megapascal. This meant the result showed that the design of thick flange considered to be fast and safe to design. Next, for the thin flange, I justify that the stress show the value is above the allowable stress of the material, which means it's considered failed to design the walnut flange. Next, I will show you the result of using the ANSYS method. As you can see here, this is the thick flange that I have designed according to the specification. This is show that the outside diameter of hub flange experience higher maximum stress at the outside diameter of the hub. This is expected as the boat load tend to rotate the flange ring in the positive direction of z-axis. Thus, this area experience overstress but does not exist through entire cross-section. As the result, we can get the final value of von Mises stresses after done the converge test. Due to the standard SME for pipe flange and pipe fitting, the safety factor of the flange must exceed 3 and 0 and above. And for these cases, we can get the safety factor of 4.20, which higher than 3.0, means the thick flange that designed in the ANSYS considered to be passed. Next, this is for thin flange safety factor where it considered to get 1.38, which is considered it to be fail condition. So after done the analysis between ANSYS and SME, I can have the comparative result between these flanges of thick and thin flange. By refer to the comparative table of the thick flange, it is shown that by using the both method, it will produce the same result which the flange is considered to be passed to design. Next, this is for the thin flange. Due to this comparative table, we can see that the flange are failed to design, even using different of method analysis. Thus, we can observe that the result of the stresses. Thus, we can observe that both methods of stresses actually experience the same outcome, even the result of the stress between both methods produce slightly different of value because on how we interpret the result are different. Which means by doing the SME, we compare to the allowable stress directly. By using the ANSYS, we compare to the safety factor, but yet it still get the same outcome. After done the comparative study, so I can develop the tool in order to achieve my objective to design the flash directly without manual designing. So I have done a tool where we can just simply design the flash using our phone by just inserting the initial parameter like design pressure, design temperature and flange thickness as the initial parameter from the specification of the client. Then everything will compute directly. So this show the figure that I designed using the tools that need to insert by the client. Then this is the parameter that actually we need to refer using the table. And lastly, we can get the outcome of the result to show either the flash that we design and the parameter that we insert at the initial state will produce the pass or fail condition of the flash design. This is about the tools. Thus, by using the tools, it's actually helpful to the manufacturer to save their time and avoid any mistake error from the manual calculation. By just using the phone, they actually can design the flange successfully to identify either the parameter that insert in the initial state can produce a safe or fail flange design. So it can save their design without do the manual calculation. So this tool will help them to calculate it directly without any manual calculation. I think that's all for this chapter. Next, we move to last chapter of chapter 5 that include further conclusion. So, for this project, I able to develop a tool to determine a safe and optimized design of wellnut flange of low velocity by directly calculated. By comparing the stress value and result that obtained from SME and SC, I able to validate that the structural analysis of flange based on both methods achieve the target of this topic to obtain the similar outcome. That's all for the conclusion. So this is the reference that I want to show you that I do, then I refer during this project. First, the main reference that I refer to the SME for Pressure Vessel Division 2. Next, I refer to the American Society of Mechanical Engineering SME B60.5 for pipe flash and flash fitting. Next, I refer the Pressure Vessel Handbook to guide me during the manual designing. And lastly, I analysis the final element analysis using the NC Workbench for student version 2019. Below is the link for my tool that we can refer to the website. I think we already end of this presentation, and that's all from me. Thank you very much for lending your time for my presentation. See you.